This video is going to review the first couple sections in Chapter 8, which were all about exponential growth and decay. And if you remember, we actually did the sections in one day because they are so similar. Rather than splitting it up and do one day growth, one day decay, it is best to just talk about them side by side. So what you're going to see in this video is we're going to go through two graphing problems where you're not only coming up with the picture of the graph using your calculator, but also answering a series of questions, and then two word problems that use either growth or decay and different models that we worked with in class. So we're going to start with basic graphing, and this is what you're going to see when you take a test or quiz. You're going to start off with an equation, you're going to need to use your calculator to graph it, and then you're going to answer a series of questions. And I have listed the most common things that are asked, which are the domain and range of the function, wherever the asymptote is, and then what the y-intercept is. And your calculator does a lot of this really for you and kind of help guide you. So the first thing you want to do when faced with these problems is to graph it. So pull out your calculator, go to your y equals. Make sure you type it in correctly. You don't want to have a typing error be the reason you miss something. So 2 to the x minus 3 power. Remember, if you have an older calculator that doesn't automatically raise it, you do have to put the power in parentheses. And then plus 1. Depending on the last thing you graph, you may need to rezoom. So I'm going to zoom 6 just to make sure I'm looking at my basic 10 by 10 window. First question that may be asked, sometimes it's not asked, it's kind of understood, is it a growth or a decay? And you can tell very obviously when you look at the picture that this is a growth graph because it's going up dramatically. My domain, the nice thing about exponential growth and decay, it doesn't matter what's going on with your graph, your domain is always all real numbers. That is true of any exponential growth, any exponential decay, whether you have shifted it, whether you've flipped it, the domain does not change. Essentially what that means is you can put any x value into any exponential growth or decay model. Your range is always going to be either above or below the asymptote. And sometimes I do the asymptote first. I kind of go a little bit out of order. Your asymptote is going to be a y value, y equals. It's a horizontal line. And the nice thing is you can see it in the picture, but you can also look at your equation. Your asymptote is going to be whatever number is being added or subtracted at the end of your function. So my asymptote is at y equals 1. You can't just write the number 1. You have to write y equals 1 because it's a line. It's a line that the graph's approaching. So to show that in my picture, I'm going to draw a dotted line right along y equals 1. Remember, an asymptote means a line that the graph approaches. And then my range, you can look at your picture, your range is either going to be above or below that number. And if you notice on this one you're looking at, everything is contained above the line y equals 1. So my range is y is greater than or not or equal to, greater than 1. It will not be or equal to. Out of habit, I started writing the or equal to. It will just be greater than 1 because it's everything that's above that asymptote. If you want to write it in more of an interval notation, you could say it's from 1 to infinity. You don't have to. You can just write y greater than 1 if you like. And then finally, your y-intercept. Your calculator does that for you as well. When you're on your graph, if you hit the trace button, a lot of times it will already be at 0. If it's not, for some reason, if your cursor's off, you can just hit 0 and enter, and it will tell you exactly where your y-intercept is. We want to write it as a point. It's the point 0, 1.125. So I'm going to graph that on my picture, just above this asymptote. And then when I draw it, I'm just going to draw the general shape, the idea that it goes through this asymptote, goes above the asymptote, through the y-intercept, and then has a dramatic increase. So that's what you're looking at for full credit. You can draw a picture that's pretty accurate. You can come up with your domain, which is always all real numbers. You get your asymptote, determine if your range is above or below that asymptote by looking at the picture, and then your y-intercept by using your calculator. We're going to do one more, and you'll notice it's the exact same series of questions that I'm asking. So again, we always want to start by going to our calculator and typing in the equation. And again, make sure you type it in correctly. So 2 times, you can either use parentheses or you can times 1/3 to the x power, and then minus 3. Hit graph. This one, if you're asked to define which one it is, this is an exponential decay graph because you're having a sharp decrease. Your graph is actually dropping. My domain is still all real numbers. I'm going to start with the asymptote again. So my domain is all real numbers. My asymptote is going to come from this line at this number at the end. It is y equals -3. So on my graph, I'm going to draw a dotted line along y equals -3. My range, if you look at your graph, again, is above the asymptote. So my range is going to be y is greater than -3. If you want, you could write it from -3 to infinity. My y-intercept, I'm going to do with the calculator, hit trace. Should already be there. It's at 0, -1. So on my graph, I'm going to put a point there. And over here, I'm going to write 0, -1. And then when I draw my graph, just going to kind of connect the dots. Really, it's just a matter of showing the correct shape. You have a sharp decrease. You're going through your y-intercept, and then you should be flattening out, kind of hovering right over that asymptote. If you want to get more specific, you can look at a table of data to kind of see more points. But as long as you have the general shape, you have your asymptote. You should not cross over that asymptote. You should kind of hover above it or below it if it's coming up towards it. And you should have the right y-intercept. The second thing that we did with exponential growth and decay is we did some modeling, exponential model or growth decay models. The idea that we can look at a situation that is either increasing or decreasing exponentially. We can write a model, use the model to make a determination of how much something's going to be worth or what the population is going to be after a certain amount of time, and then use the graph of the model to make a prediction about what's happening in the future. So I have two separate problems. I decided to do one that's growing and one that's decaying, showing you kind of two different types of problems that we would have done in class. So the first one's talking about buying a stereo system for $750, and each year the value of the stereo system is decreasing. Another word that you might see is depreciating, the idea that it's losing value. So the first thing I need to do is write a model. So my model will be the initial amount, which is $750, times 1 minus 5%. Remember, you need to think of that as 0.05, or you can write it as just 0.95 when you subtract, to the t power. Or if you write to the x power, that's fine. A lot of times we'll use t, though, because we're representing time. So that's my model. To figure out how much it's worth after 5 years, I am just putting a 5 in for t. So this is going to be very much just kind of plug and chug with your calculator. So I'm going to write down the work, and then I'm going to go to the calculator and figure out my answer. So we're going to get out of this graph. We have 750 times 0.95 to the 5th power. It is money, so I can round to the nearest penny. It's going to be worth $580 and about 33 or 34 cents. Oh, copied that wrong. 580, not 84. $580.34. And then finally, the last question that's usually asked is, now that we have the model, we are going to use a graph of the model to make a prediction. And we want to use the graph to determine how many years it's going to take for that stereo system only to be worth $400. Now, logically speaking, we know it's more than 5 years, because in 5 years, the stereo is down to $580, but still hasn't come close to only $400. So it's going to be somewhere after 5 years. So what I do for this is I'm going to go to my y equals and graph my model. So my model is the very first thing you wrote. So 750 times 0.95 to the x power. You've got to put an x there. The temptation is to put a number there. If you put a number there, you're just going to see a flat horizontal line. And then in the next line, you want to put what you're trying to reach, what your kind of target number is. So my target number here is 400. Now, if you hit graph right now, you're not going to see anything, because currently my window is a basic 10 by 10 window. I need to be looking at something that's over 400 as far as my y. I need to look at something that could be several years down the road. So I'm going to go to my window and make some adjustments. First of all, my minimums have to be 0, because x minimum is representing the start of the time scenario. We're starting at 0. I'm not sure x maximum. I'm not sure how many years, so I'm going to keep it at 10. I might change it later if I don't see a good picture in my graph. My y minimum is also 0. That is the value of my stereo. And my maximum, well, I want to get to $400. One thing you could put, you know it's never going to be any higher than $750. So if you want to put $750, you'll see the entire graph. If you want to put something like $500, $600, as long as it's above that target number, you'll see everything you need in your window. So hit graph. So here is the value of the stereo steadily decreasing. Once that's done, you'll see your target. Now, I didn't get to see where they intersect. My goal is to see where they intersect. So I'm going to go to my window, and I'm going to go a little bit further over in X. So instead of doing 10 years, I'm going to see what happens after 15 years, and hit graph again. And that's the nice thing, is if you hit graph and you don't see what you want to see, you can adjust it. You can go back to window and say, well, I didn't see far enough over or high enough. So right where they intersect, that is going to be your answer. Nice thing is your calculator finds the intersection for you. If you hit second and trace, go to intersect, it's the 5th one down. It'll ask you for the different curves. Well, you only have 2 curves to begin with, so you can hit enter, enter, and enter. And when you're done, it should say the word intersection. This tells me, if you look in the bottom left-hand corner of your calculator, that it takes a little over 12 years, 12.255 years, in order to get a value of $400. So my answer, 12.255, is years. make sure your answer makes sense. If you would get something like 1,000 years, it's not going to make sense that it takes 1,000 years to depreciate. If you're going to get something like 2 years, that doesn't make sense either, because we know after 5 years it's still worth $580. So make sure within the context of your problem, your answer makes sense. We have one problem left, and that is dealing with our compound interest formula. Let me write down the compound interest formula for you to remind you how it worked. This was our compound interest formula. P stands for principal. It's the amount that you're actually investing. R stands for interest rate. You have to write it as a decimal. N stands for the number of compoundings. That is how many times per year do we compound our interest. We could be doing it daily, quarterly, annually, semi-annually. And then T stands for time. So in this particular problem, we are investing $2,000. So that's our P, our principal. Our interest rate is 6.5%, so 0.065. So I'm going to have 1 plus 0.065. We are compounding quarterly. Quarterly means 4 times a year. So we're going to put a 4 here. And then my exponent is going to be 4 times t, or 4 times x. So that's my model. Second part is using the model, the plug and chug idea. We're taking that model and we're going to plug a 5 in there for time. So we're going to put a 5 right there. So really I'm going to do this on my calculator, make short work of it. So get out of this graph. So 2,000 times 1 plus 0.065 divided by 4. And then my exponent, you want to type it in as 20. You could do 4 times 5, but if you're using an older calculator, you'd have to put it in parentheses. So I think it's a little easier, less chance of mistake if you just type in 20. So after 5 years, I have $2,760.84. And then finally, in the last part, we're making a prediction again, using the graph. We want to figure out how long it's going to take my money to double. So on my calculator, I'm going to graph my model in one line, and I'm going to graph my target amount, which is doubling up to 4,000 in the next one. So get rid of what I have here. So my model this time is 2,000 times 1 plus 0.065 divided by 4 to the 4t power. In this case, we're going to type 4x. If you have an older calculator, you have to put the 4x in its own parentheses. And then my target amount, I want to double. So if I started with 2,000, I want to get up to 4,000. I'm going to change my window because I'm dealing with very different amounts than I was for my stereo system example. I want to know how long it takes to double. Well, you can tell in the first one what we just did. It took 5 years and it gained about $760. So I'm not sure how many years it's going to take. I'm going to leave it at 15. We could make it go all the way to 20. We can make it a little less. Until I see it, I'm not going to change that. I am going to have to change my Y maximum though, because I need to get all the way to $4,000. So I need my Y maximum to be bigger than that. So I'm going to make it 4,200. You can make it 4,500. It has to be bigger than 4,000. So here is my money growing with my interest rate. And then here is my target amount. So you'll see I actually don't have to change my window. I can see the intersection point on my screen. So I'm going to go to second, trace. It'll get the calculate menu, intersect. Have to hit enter 3 times. Should have the word intersection when I'm done. So here it shows me that it's going to take 10.75 years in order to get to $4,000. So I'm going to write it 10.750 years. And again, make sure your answer makes sense. It shouldn't take thousands of years to double. It also shouldn't double overnight. So you want to make sure that within the context that your answer seems logical. So this takes you through everything that you should know how to do for 8.1 and 8.2. Notice it's very calculator based. You should be able to use the calculator to help you come up with graphs. You should also use the calculator to help you make predictions and use models. So with that, you have a tremendous tool to help you with these sections.